Today we are going to talk about the H hydrogen NMR spectrum. So bear in mind, only the atoms that consist of odd number of proton or odd mass, it can form the NMR. So we have carbon 30 NMR, we have hydrogen NMR, but we will no longer have any NMR spectrum with the even number of mass of the atoms. So specifically, we are going to discuss about the proton NMR, also known as the HNMR spectrum. Basically, we can use two words to describe it: spin, fleet. So we know that in hydrogen we have one proton, right? So say that this is the proton. So this proton, it can spin in two directions. The first direction will be clockwise and the other direction will be anti-clockwise. So if we have many hydrogen that they eventually spin in different directions, so what is going to happen is when we apply an external magnetic field, the spinning of the hydrogen will align. Most of them will align with the external sources, but minority of them will against the external magnetic field. It's like humans, some of them will follow the trend, but some of us will not. So what's happened is, if we apply an external energy into the molecules, into the atoms, the hydrogen atoms, they are going to absorb those energy and flip. A spin flip will occur. That means that if we apply enough amount of energy, what's going to happen is, so this is the energy we put into, that is sufficient enough for them to occur the spin flip. Spin flip occurs, so all of them is going to go against the magnetic field. So all of them is going to against the magnetic field, and the energy that is needed for them to occur the spin flip is measured and calculated by the system, and hence giving us an NMR spectrum. And we'll use this to determine the structure of the compound. Now the second thing I want you guys to understand is, there are different types of hydrogen in terms of their environment. So for example, we have a propanol. So this structure actually consists of four types of hydrogen. The first type will be the OH, because this H is connect with an O. And the other type is this two, which is bonded with a C that connect with a C and O. And the third type will be this two that is connect with this carbon that adjacent to two carbon. And the last type is going to be this three, which is bonded to a carbon adjacent to another carbon which bonded to two hydrogen. And these four types of hydrogen will experience different environment and different electron density, and giving us different types of signal in the spectrum, in the NMR spectrum. So based on this compound, what can we observe is it has four types of hydrogen, right? So what we will get is four signal in the diagram, or in other words, the number of signal in the diagram will help us to determine how many types of hydrogen are there in our compound. So the second message we want to observe is the chemical shift. Because each hydrogen have different surrounding environment, so their chemical shift will be different, and therefore we can use this chemical shift to determine their partial structure, and later you will know how it looks like. And the second message that you can get from the NMR spectrum is the integration. And this integration, or the area under the graph, give us the number of hydrogen in that specific environment within. And finally, the message that we are going to look on is the spin splitting. By looking at this, you can know the carbon, the neighboring carbon. By looking at it, you can know the number of hydrogen on the neighboring carbon. And there are some special things that I want you guys to keep in mind. The first one is, if this one is not considered as carbon, is not considered as a neighbor, because a neighbor should consist of a same carbon. So this structure could possibly becomes a neighbor, but if their structure looks identical, then it's not considered as a neighbor. You can't be your own neighbor, right? So these two carbon are not a neighbor, cannot consider be able neighbor, but if we change it to OH, now they are not the same, then we can say that it is neighbor. So first thing first, the carbon, the element that connect them should be the same. And secondly, their surrounding environment should be different, and hence it could be identified as the neighbor. So now let's look on to the real diagram, what it looks like. So this is our data sheet that is going to be provided, and this, as you can see here, the chemical shift, it will help us to determine the partial structure, and those are the hydrogens that are in that environment that can giving us some it's like a piece of small puzzle, and we have to collect all those and connect them together. So it's not easy, but I will guide you through how to do that. Here's how the question looks like, and you will always see a peak at 0, which is the reference, and it's called the TMS, tetramethylsilane, and the hydrogen in this compound will be exactly the same environment and give us the peak. So that's why you will see 0. We set it as a reference. So everything is based on this compound. Alright, now looking through the whole diagram, we can see 4 peaks, indicates that there will be 4 types of hydrogen. Am I right? Now we can note down its chemical shift, and that will help you to gain marks on the exam as well. Chemical shift is its integration number and its splitting pattern, okay, and therefore giving us the partial structure. So the first one, we can see that this peak is approximately 1.0, and its integration is up to 3. That means we have 3 hydrogen under the same environment, and the splitting pattern is triplet, and that indicates that we will have 2 hydrogen on our neighboring carbon. So chemical shift on 1.0, we can look to our data sheet. 1.0, it could be this one, it could be this one, but somehow if you look through our molecular formula, C9H12, it has no oxygen at all, so, and nitrogen as well, so we can eliminate this possibility, and that gives us the final structure, which is RCH3. So we can write here RCH3. Now it is also same as this one, integration up to 3. There are 3 hydrogen under this environment, but what could the R be? Now we look at the splitting pattern. It consists of 2 hydrogen, right? It will always n plus 1. So if the neighboring carbon has 2 hydrogen, it will show you as triplet. If it has 3 hydrogen, it will show you as quartet. So since it's triplet, that means we'll have neighboring hydrogen of 2. And with that say, this hydrogen should connect with 2 hydrogen, and we don't know yet the other one. And that's how the partial structure can be determined. Now we look at the second peak now. It is approximately 1.7 or 1.6. Integration up to 2, and the splitting pattern is 1, 2, 3, 4, 5, 6. We can see it as sextet. At 1.6, we look at the data sheet. So it could be this one, it could be this one, but no oxygen, no nitrogen, so we eliminate. It could be this one as well. But the problem is we need 2 hydrogen. So in this, we already have 3 hydrogen, so we can eliminate this possibility. It only can be this one. So if let's say, but this one only have 1 hydrogen, that means that we need 2 equivalent of this one to give us 2 hydrogen with this environment. So 2. So what could be the R? As you can see that it's sextet, right? So it means the neighboring carbon should have 5 hydrogen total. So we can't determine this one, so we can just leave it first. Now the third peak, it gives us approximately 2.7, and integration of 2 with triplet. So what's going to get is this, refer to this 2.7, could be this one, no, because don't have nitrogen, so the only possibility is this one, because we don't have oxygen. Now integration to 2, that means CH2R is preferably, or else we will have 2 moles of this one. It will exceed the carbon that we have, so the only possibility is 2 hydrogen, this one. So we draw it out, benzene ring attached with a CH2 with R group. So what could be the R? Triplet. As you can see here, this carbon will have no hydrogen at all. That means this carbon will have 2 hydrogen, and it attached to mystery. Now the last peak is 7.0 approximately, and in integration of 5 singlet. And if you look through the data, 7.0, not this one, not this one, the only possibility is this one, so this hydrogen. But as you can see here, we only have 5, so that means 1 is substituted. So what could it be? The only possibility is it connect with this one. Now we're trying to solve the whole puzzle because it's R and it's similar with this one, right? So it could connect with this one, CH2, this, and then we look at this one. The other end would be CH3, right? Now how many carbon that we have used up? 1, 2, 3, 4, 5, 6, 7, 8. We only have one more carbon to insert it, and the total number of hydrogen would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It also matches with our molecular formula. And we have 4 types of hydrogen as well. One is this one, 2, 3, and 4. Alright. Now you may wonder why or how come this structure exists. So that means we actually got a wrong answer, because this benzene ring, particularly this carbon, is going to be deshielding, because this benzylic carbon is sp2 hybridized, and sp2 hybridized is more electronegativity than the sp3, which is the neighboring carbon. Because of the increase of s characters, the electron will held in place. So this carbon particularly is going to be affected by this one. And remember that we have an electron donating group here, so the overall electron movement will be moved toward the left side, and that means this carbon is going to be downshielding. Downshielding basically means that when the electron is being pulled by the more electron negative atoms, it will be more exposed to the energy. So that's why I call deshielding. And when deshielding occurs, downfield will occur as well. Downfield basically means that the ppm value will be moved more toward the left side, and that's why it gives us 1.6. And in reality, this RCH2R is going to get, but it out of range. The data we get is out of range is 1.6. That is because the deshielding effect. So actually at here, we will get, the structure we will get is this one. This is the carbon here, middle carbon, that is being pulled by the benzylic carbon and donate the electron group by the methyl group. And that's why this carbon, sorry, just now I say wrongly, this carbon actually referring to this carbon, and the R group over here and here is match up. And that's how the proton NMR works and how we analyze this information to get the desired structure.